Hello everyone, my name's James Pruitt and this is my fourth lecture on generating functions, and I'm going to stick with the algebra of sequences. And let me write what we have so far. Our ring, let me define our ring real quick that we're working with. This is the set of sequences um, whose range is the complex number, and we defined an addition between sequences. And that's just component-wise addition. We add the corresponding terms to get the sum, and we defined a multiplication between sequences as let me write this down real quick and talk about it. And what we do is we have a sequence here, the a sub n's, we pick one, and then we find the corresponding one who and you look at the indices, and if this corresponding pair's indices add to n, then we multiply them together and we include that in the sum. And there's only a finite number of these because all these indices are non-negative integers. Okay, this is our ring. This is our algebraic structure, and this is what we're working with. And last time, let me leave that up for a second. Last time, we looked at this sequence whose generating function is 1 minus x. And that's the sequence. If that's the sequence a(n), then a0 is equal to 1, a1 is equal to negative 1, an is equal to 0 for n greater than n greater than 1. And we found its multiplicative inverse. And if bn is the multiplicative inverse of an, we found it to be that bn is equal to 1. And the generating function of that is just 1 plus x squared plus x cubed plus dot dot dot. And we're going to continue with this finding multiplicative inverses. So we're going to look at this new sequence whose generating function is 1 minus cx, and we're going to call that sequence an, and we're going to have so a0 is equal to 1, a1 is equal to negative c, and an is equal to 0 for n greater than 1. And c is just any arbitrary complex number. We're not too concerned with that. So what we want to do is follow the process. I described a process to compute multiplicative inverses last time in my theorem that I proved about sequences with non-zero constant terms having a multiplicative inverse. I described a process, and I'm going to follow that description. So I want to get rid of this cx term, so I multiply 1 plus cx. And when I multiply that out, I get, okay, there's a 1, there's a cx, and then there's a minus cx, which cancel each other out. And then when I multiply them, I get minus c squared x squared, just like the process I described last time. And then I got 1. I'm going to multiply by 1 plus c squared x squared to get rid of that term, and that's going to be 1 plus cx, 1 minus cx. Yeah. And that's going to equal to 1. You got a negative c squared x squared times 1 plus c squared x squared, and they cancel out. And then we multiply the last two, and we get minus c to the fourth x to the fourth. Okay, and so I want to get rid of this x to the fourth term here, so I multiply by 1 plus c squared. Okay, 1 plus c to the fourth x to the fourth. it's going to be 1 plus c squared x squared times 1 plus cx times 1 minus cx, and that's going to equal to 1 minus c to the 8th x to the 8th. Like I said last time, this process, this quasi-algorithm, continues on forever. So it doesn't look like I'm going to ever stop. So what I want to do, I've got this sort of this product here who's working up to be the multiplicative inverse of this. And I want to do is I want to multiply, go ahead and multiply this out and see if it gives me any ideals, because I want to make a guess. And it's all right to guess. We do that in, when we integrate. We sort of, we don't, there's an algorithm for integration, but it's so difficult there's no way you can do it in your head. So what you do, you just guess, and then you take the derivative and you can check to see if you, by the fundamental theorem of calculus, you can check to see if your guess is correct. So guessing is fine. So we'll make a guess, and then we have our definitions for multiplication that we can multiply this, our guess, times our sequence, and if we get the multiplicative identity, we got it right. If we don't, we have to make another guess. We have to figure out another way to solve this problem. So I'm going to multiply this out with the hope that it's going to help motivate my guess here. So we're going to say 1 plus c to the 4th x to the 4th times 1 plus c squared x squared times 1 plus cx. And that's going to equal to, I'm going to multiply the first two terms out, and that's 1 plus c to the 4th x to the 4th, and we're going to get 1 plus cx plus c squared x squared plus c cubed x cubed. And that's going to equal to, and then when I multiply that out, I'm going to get 1 plus cx plus c squared x squared plus c cubed x cubed plus c4x4 plus c5x5 plus c6x6 plus c7x7. Okay, that looks like right. C4, C5, C6. So this, what it looks like to me, if I was to make a guess, this is part way in the construction of my multiplicative inverse of 1 minus cx. I'm trying to find the multiplicative inverse of 1 minus cx. And following the construction I described last time, I produced this polynomial. And so I'm looking at that, and I'm saying I see a pattern, and I'm going to guess that the multiplicative inverse of this is the sequence b sub n equal to c sub n, or the sequence b sub n defined by this relationship. And I'm going to guess that that's the multiplicative inverse of our a sub n, which is a0 is equal to 1, a1 equal to negative c, an equal to 0, n greater than 1. So what we do is we define another sequence, and we're going to let this sequence, I want to use c sub n, but that might be confusing. How about let's go to d sub n. I hope that doesn't confuse anybody. D sub n is equal to a sub n times b sub n. So like you do with integration, you guess an answer, and then you take the derivative, and by the fundamental theorem of calculus, if the derivative equals the integrand, you've got the right guess. You made the right guess. So we've guessed this sequence, so all we have to do is multiply this sequence by that sequence, and if dn turns out to be the multiplicative identity, our guess was correct. Let's see if we can do this. If we look at this sequence A0 and A1, they're just two two non-zero. If we look at the sequence A, there's only two terms that are non-zero. So there's only two terms we have to worry about because 0 cancels the others out. So we look at D0, and that's A0, B0. And that's just A0 is 1, and C to the 0th power is 1, so that's just 1. So far so good. D1 is equal to A0 B1 plus A1 B0, and that's equal to 1 B1 is C plus A1 is negative C, and B0 is C to the 0, which is 1. So that's equal to C minus C, which is equal to 0, which is still good. That's what we want. So now we can do the general formula, which is D sub n, and that's equal to A sub 0. There's only two A non-zero terms, A0 and A1. So that's the only ones that's possible to show up in our sum. So that's going to be B sub n plus A1 times B to n minus 1. So that's going to give us A0 is 1, B to the n is C to the n, plus A1 is negative C, and B to the n minus 1 is C to the n minus 1. So that's equal to C to the n minus C times C to the n minus 1 is C to the n, so that's equal to 0. And so we're done. So Dn is the multiplicative identity. And our guess that that the multiplicative inverse of 1 minus cx. Let's see how we want to write that. Okay, let me erase this. State that a little more clearly. I'm going to just say this. The generating function of the multiplicative inverse of 1 minus cx is equal to is 1 plus cx plus c squared x squared plus c cubed x cubed plus ... Okay, that's what I wanted to do for this lecture. I'll continue on the next lecture. Thanks.